Okay, we've been doing descriptive statistics, and now we're going to move into the concept of inferential statistics. And when we move into inferential statistics, basically what we're trying to do is we're trying to make statements and draw conclusions about our data beyond just the immediate descriptions. It's going to be important for us to review some of these concepts that we learned in research last semester as we move into inferential statistics, because you're going to have some of these basic concepts to be able to know which tests to run and how to interpret the test that you're going to run. So I'm going to start this section doing some defining of inferential statistics and explaining of it, but I'm also going to review some of those basic concepts that we learned last semester. Your homework for this time is going to be to complete a worksheet defining and giving examples of some of those concepts. Then you'll have that worksheet that you can work with as we move forward and work in Excel to do these inferential statistics on our database that we're practicing with. Okay, so first of all, let's think about our descriptive statistics that we've been working on. And we've been using these to actually describe the basic features or those attributes of our population, our sample population. Our descriptive statistics have provided us with simple summaries about the sample and the measures that we've been using. So in the homework number 2, you broke down your analysis for the client population that we're using based on job title and based on marital status, and you looked at work-life balance based on those attributes, and you looked at age based on those attributes. You got a description for the overall age of the group. You got a description for the overall work-life summary of the group. So you had a pretty good idea of what your sample population looked like using those descriptive measures. And we use those descriptive measures because we simply want to describe what is or what our data shows. We use it to bring the quantitative descriptions down into a manageable form, something that makes sense, and help us to simplify those large amounts of data in a sensible way. That's what we've done up to this point in this class. So now as we move into inferential statistics, we're actually going to try and reach beyond those conclusions, and we're going to begin to inferring some information about our sample data and what the population might think. We use these to make judgments about the probability that something that we've observed or a difference that we've observed between two groups is a dependable one, or did this happen by chance? And then we use inferential statistics from our data to make more general statements about more general conditions. So inferential takes this analysis up one step. When you move into inferential statistics, there is a lot of information behind this in terms of assumptions about statistical tests. This is where the bell curve that you've learned about in the past, the normal curve, comes into play. It comes into the probability of being able to say that something happened for a reason and not by chance. We are not going to get into all of that in depth. All I'm going to show you the rest of this semester is the basic inferential test that we use in social work to be able to explain or make sense out of data that we're using with our clients. If you're going to get into more academic research and make statements beyond a sample population that are generalizable, you're going to have a much more in-depth understanding of statistical analysis and the rich theoretical aspects that go behind this. But for what you do in a day-to-day practice and from a practical standpoint, what we learn in the next few weeks is going to be very useful for you. And again, we're going to do these in Excel because that is something you're going to have access to be able to use while you're in your practice settings. We use inferential statistics when we have developed and employed an experimental or a quasi-experimental design or in a program evaluation. And again, what we learned last semester is the basic difference between an experimental design and a quasi-experimental design has to do with the random assignment of individuals to groups, something that we don't normally do in social work practice. And in our program evaluations, we actually just use the research designs that we learned about in doing a program evaluation. So some of the quasi-experimental designs that we've learned about are going to include pre-test, post-test of a group that's not randomly assigned, or comparison of groups that are not randomly assigned. We also have used the pre-experimental designs, or the pre-quasi-experimental designs, where they put the survey research into that, and the researchers now define survey research as being a pre-experimental design. And what we're going to do with the data that we're using in our example, our hypothetical example, is we're going to use some of that survey data and employ these inferential statistics tests just to look to see if there's relationships between these variables. What we're doing doesn't uphold to the real rigor of statistical analysis in terms of what publications might look like. But again, it's very useful and very informative for what we're going to be doing in our practice settings. So you're going to need to go back and you're going to need to review what an experimental design is and what a quasi-experimental design is. So you'll have that understanding of how to apply inferential statistics moving forward. And as I indicated, the basic difference between this has to do with the random assignment, because we're usually looking at differences in groups. If you're in a practice setting, you're going to want to know if one of your treatment interventions is more effective than the other one, or you're going to want to know outcomes of a group based on a particular variable so you can make decisions about your practice. So we're going to be using quasi-experimental designs, research designs in our day-to-day practice, because we're not going to set up a formal study and randomly assign individuals to two different groups in order to be able to test this. It's virtually, unless you're doing, again, academic level research, quasi-experimental designs is what we're using in our day-to-day practice. In inferential statistics, we actually use the concept of statistical significance. And if you remember, I've told you a couple of different times that semantics in research is very important. And we don't, in writing our literature reviews and writing results and writing things like that, we don't use the term significance unless we're going to be referring to statistical significance. So this is what we're going to get into in inferential statistics. And basically, we use statistical significance to help us quantify, assign a number to, whether a result that we see is likely due to chance or to some factor of interest. Is there meaning behind that relationship we're seeing in those variables, or did it just happen by chance? That's breaking down statistical significance into just what it means. That's what we're attempting to do. We want to know that our clients improved because of the intervention that we were providing, and not just because it was some fluke or some random chance that they got better. We need to be able to say with evidence that the interventions we're providing is making a difference in the client's lives. And we use statistics and this statistical significance to be able to say that with supporting numbers or quantify it. So when we're going to be using statistical significance, we're going to go back to when we were designing our research study or when we're designing our program evaluation. And we start with by stating the research hypothesis. We're going to review that again. We have a null hypothesis. We select a probability of error, or what's called an alpha. And then we select and compute the statistical test for significance, and then we interpret those results. So when you're doing the research aspect of it, this is exactly the steps that you would go through in terms of setting up to do your statistical analysis. If we're using a pre-experimental design and we're using a questionnaire in a survey design, we're not necessarily going to have stated research hypotheses. We might, but we may not have that at the very beginning. But what we're going to see is if we want to run a statistical test or an inferential test to test the relationship between a couple of variables on that, we will actually then state a research hypothesis. Ideally, when you set up your study, you're going to have that you're going to have the research hypothesis stated ahead of time. which then goes with your null hypothesis, and then this is what you'll be testing when you do your statistical analysis. So let's review again. A research hypothesis is a specific, clear, and testable proposition or predictive statement about the possible outcome of scientific research study based on a particular property of a population, such as presumed difference between groups on a variable or relationships between variables. That's got a lot of words in it, but we're going to use an example here in a minute to help you understand what that is. It's a statement of prediction, and it describes in concrete terms what we expect will happen within our population based on these variables. The other aspect that's important to know about your hypothesis is whether it's going to be one-tailed, which is directional, or two-tailed, which is non-directional. And this becomes important when you're selecting the type of test to run, especially the t-test in Excel, because you have to select whether you're running a one-tail or a directional hypothesis, or a two-tail or a non-directional hypothesis. And again, we're going to have some examples for this, but you need to understand the difference here. So if I'm making a statement or a hypothesis about the relationship between two variables in my sample population, and it's one-tailed or directional, it means that prediction is made regarding either it's a positive or negative change relationship or difference between the two variables. So I'm going to be very specific about what that relationship looks like. If it's a two-tailed hypothesis, then we don't predict the direction or the difference or the relationship. And again, I'm going to give you an example in a minute, and I think that will help a lot here. The one-tail and the two-tailed, when we're talking about that, if you remember in the normal bell curve, the normal curve, you have the tails at the end of it. So you have where everybody falls in the middle, or the majority of individuals fall in the middle. And then as the curve goes out, you have the tails on the end. So this is whether what this is referring to, one-tailed or two-tailed, directional or non-directional, is where your results may fall. And so just think about the theoretical picture of that bell curve, and that's what it means, one-tailed or two-tailed. But it's actually called directional or non-directional hypothesis. So you're going to have to know how to make a hypothesis statement or research hypothesis statement, and whether it's going to be one-tailed or two-tailed. And these decisions have to be known and have to be made before you select your test to run, because it's going to direct you as to which test is appropriate to run. So let's break this down in terms of the data that we've been using for our homework. Right now we're exploring the relationship between work-life balance using your work-life scale and job titles. And we have the job titles of administrators and social workers and case managers and drivers and clerks and cooks. So we're going to say that we expect, based on the literature and other evidence that we gathered when we were designing our study, that in our sample, those who hold higher stress job titles will experience lower work-life balance. And we want to test this. This is our research hypothesis, okay? So we're going to make the statement, administrators, because we've determined those are higher stress jobs, in our sample population will have lower levels of work-life balance when compared to drivers, which research shows us has lower stress jobs in our sample. So we make that statement again, administrators in our sample population will have lower levels of work-life balance when compared to drivers in our sample population. This is a directional. We're actually stating that administrators are going to have lower levels of work-life balance. So we're demonstrating exactly where the direction of work-life balance is going to go. We say it's going to go lower when we compare it to drivers. So it's one direction. It's just one direction. The null hypothesis is really what we test. And we test that there's no difference in work-life balance in our sample population based on job title. So the research hypothesis states what we're looking for or what we expect to happen, and the null hypothesis simply states there's no difference. It's the hypothesis of no difference. So let's look and see what a research hypothesis is going to look like for a non-directional statement. So again, we're exploring the relationship between work-life balance and job title. We expect, based on research literature and other evidence, that there will be a difference in work-life balance between drivers and cooks. We just expect there's going to be a difference there based on the evidence that we took out of the literature. These are both fairly equal in stress, so we're just going to say there's a difference between the two, but we're not going to say what direction that difference is going to be. We're not going to say cooks are going to have higher or lower work-life balance than drivers. We're just going to say there's a difference. So our research hypothesis, which is non-directional, is going to say there's a difference in work-life balance between drivers and cooks in our sample population. That's simple. The null hypothesis, there is no difference in work-life balance in our sample population based on job title. It's the hypothesis of no difference. So this is a non-directional hypothesis. We're just saying we're going to find a difference, but we're not saying what direction it's going to be. Whether you choose to make a statement about a directional or a non-directional hypothesis is going to be supported by the literature and the evidence in the relationship you're looking for between the two variables. The two variables right here we're looking at is work-life balance and job title. In the first example, we said that we actually had research evidence to show us that administrators have higher stress levels than drivers. So we would expect that they would have lower levels of work-life balance. Again, it's based on what we already know. That's why that all-important literature review happens before you set up your research study, because it sets those parameters of what you're going to be able to look at once you gather your data in terms of the relationship in those variables. So we can't just make this up as we go. That's where this all comes and it becomes tied together. So I've given you an example of a research hypothesis that's directional and one that's non-directional based on the hypothetical set of client data that we're using in our examples. The next thing that we have to understand when we're doing inferential statistics is we have to understand exactly what statistical significance means and how to determine if we've achieved that or not. So we talk about terms, we talk about a p-value, and the p-value is a number, it's a probability, and we use it as a tool to challenge our initial belief, which is the null hypothesis, when the result is statistically significant. So we're going to look at a p-value in our independent samples t-test or our paired samples t-test or our ANOVA or our chi-square. We're going to look at that p-value to determine if our research hypothesis is significant, is statistically significant, or did it just happen by chance? When you hear the term alpha, it also refers to the p-value, but the alpha is your predetermined significance level or your threshold that you set before an experiment, and this is to avoid bias. So technically, when you set up your research study, you will make the statement that you're going to evaluate the relationships of the variables at an alpha level of 0.05. That's the standard for behavioral sciences. That's the standard for social work. We pretty much always look at statistical significance at a 0.05 level. And what does that mean? That essentially means that 5 times out of 100, we're going to be willing to make the mistake and say our finding is significant when it's not. Because nothing is absolute in research, we can never say with 100% that intervention A resulted in outcome A. But what we can say is we've set up our research, with such rigor and to the level that we're willing to accept 5 times out of 100 that we're going to mistakenly say intervention A resulted in the outcome of intervention A. And this can be, this is, if you think about medical science, if you think about some of the hard sciences, or even if you think about funding for us, this is a threshold that we're willing to accept of making a mistake. So we accept at the 0.05 level. The smaller your significance is, if it goes down to 0.01, 0.001, 0.000, then the stronger or the more significant that relationship is. So when we talk about statistical significance, it's the observed p-value is lower than the alpha, what we set to begin with, then we can conclude that the result is statistically significant. So if I say that I'm setting my alpha or my p-value that I'm going to use to base my judgments on is going to be 0.05, then every time I get a p-value in my statistical analysis that is 0.05 or less, it's lower than the alpha, then I can conclude that that relationship didn't happen by chance, that there's some meaning behind that relationship. And that's what we're looking for when we do our statistical analysis here for inferential statistics. Oftentimes, we look at relationships in data, and this is happening. It's just running rampant at this point in time in terms of the coronavirus and where news media are taking some statistics and they're putting them out there, and we think that they're 100% accurate, and these relationships are happening, and the scientists are cautioning us that really what they're just doing at this point is describing. They've not gotten to a level to be able to make those inferential statements about the relationship between the coronavirus and who it's most likely to create complications for, or who's most likely to die from it. This is all still evolving, and we don't have the methodology or the research methodology set up in a point where we can make those really strong statements that this is statistically significant. A lot of what is coming out right now is descriptive, and it could be purely chance that these relationships are being made or these inferences are being made. So when we talk about the 0.05 level and 5 times out of 100 we're willing to be wrong, in some areas we don't want that. We don't want to be wrong even 5 times out of 100, especially in terms of medical science and the hard sciences. We want everything to be exact. And so we want it to be at a 0.00 level or a 0.01 level. So as we're getting research and evidence about what's happening with the coronavirus and how it's impacting individuals, there has to be increased rigor in gathering that data and controlling for many variables before those statements can be made at any level of statistical significance. But too often what happens in the lay population, the non-professional population, is they hear those terms, they read that information, and they put a lot more meaning into the relationships between two variables than actually what is there. In our research, this is what we're trying to control for. We're actually trying to be able to say with substantial amount of authority and evidence when we see relationships between two variables. That's what we look for with statistical significance. And that's why we set ours at 0.05. We deal with humans. There's a lot of variables. There's a lot of extraneous variables that could be impacting the outcomes that we're seeing. But if we can actually get it down to the level where only 5 times out of 100 we'd be wrong saying there is a relationship or saying there isn't a relationship, then we're going to be comfortable with that level to call it statistically significant. So the type of tests that we're going to be running in our inferential statistics are the really common tests that are run from a behavioral standpoint, behavioral sciences standpoint, and most often used in social work research. And it's t-test, ANOVA, and chi-square. We can do all of these in Excel. We can also do multiple regression in Excel. I don't get into multiple regression because generally we don't have time in the semester to do that. If I'm able to do that, I will record a presentation for it and we'll put it up so you'll have it. But just know t-test, ANOVA, and chi-square are the most common inferential statistical tests that we're going to be using in our day-to-day practice. When we talk about the t-test, the two common ones that we use are the t-test for differences between groups, and these are independent samples t-test, oftentimes called the student t-test. And these t-tests assess whether the means of two groups are statistically different from each other. So think about that. We're talking about a mean of two groups, which is an average. So that right there tells me I need to have a variable measured at an interval ratio level because I need a mean. So I need numbers that can have statistical or that can have mathematical computations done. So we could, in our example, what we're going to look at is we're going to look at the means for age. We're going to look at the means for work-life balance, and we're going to determine, is there a statistically different level between categories of marital status or categories of job status? Would there be a statistically difference in work-life balance between administrators and drivers? So I have two independent groups. I have administrators and I have drivers, and I'm going to examine them on one test, work-life balance, and see if their mean scores are statistically significantly different from each other. Or did it just happen by chance? That's what I'm trying to determine. So this level of test is appropriate whenever you want to compare the means of two different groups, and it's especially appropriate for the analysis when we're using post-test only two-group randomized experimental design. Go back and look that one up because remember that's an experimental design, and most oftentimes we don't use that because we don't have the random assignment. But the t-test is a difference between two groups on one measure. The paired sample t-test compares the means from the same group at two different times. So maybe I want to compare the mean of work-life balance for administrators before and after I do an intervention. So if I use the pair sample t-test, I'm actually using it on one group at two different points in time. If I'm using the t-test for differences between groups, I have two groups on one measure that I'm comparing them. So you have to think about that when you're choosing which test to run. Am I looking at one group at two different times, or am I looking at two groups on the same measure? The one sample t-test is one that we don't often use in terms of our practice settings, and that's because it compares the mean of a single group against a known mean in a larger population. So this is one that we don't normally use because we're usually engaging in some form of program or practice evaluation. So we're looking at the individuals that we work with and comparing them against each other. But the one sample t-test actually it's more of an academic research approach, and it takes the mean of a single group in your research and compares it with a known mean from the population. The other test that we will be working with is analysis of variance. And the one-way analysis of variance is what we work with in this class, and it's used to determine whether there are statistically significant differences between the means of three or more independent, unrelated groups. So if I wanted to look at work-life balance and see if there's a difference in work-life balance between administrators, drivers, and cooks. I want to look at the difference between those three instead of just two of them. I would choose the ANOVA, the one-way analysis of variance. It's made to look at the difference between three groups as opposed to the independent samples t-test, which looks at the difference between two groups. They do essentially the same thing. It's just a different statistical formula used based on the number of groups. And then there's chi-square. And chi-square is where we test the independence when we are using categorical variables. So it's commonly used for testing relationships between two categorical variables, which can be nominal or ordinal level variables. So maybe we want to look at the relationships between marital status and job title in our sample population. We have some theoretical perspective that we gained from doing our literature review prior to instituting our research, that there's going to be some type of relationship between marital status and job title. And maybe we want to say that those who have lower work-life balances or based on job title. So our literature review tells us that if you're an administrator, you're more than likely going to have a lower work-life balance. So your marital status is going to be categorically different from drivers. You're going to be more likely to be divorced than drivers are. We use the chi-square statistical test to tell us if those things are independent in our sample or if they're related. Is marital status independent of job title in our sample? That's what we would look for if we're using chi-square. So just to summarize a little bit here, because we've went back to things we learned last semester that we need to remember this semester as we're moving into inferential statistics. We have to have knowledge about hypotheses, how to state the hypothesis, if it's a one-directional or a two-directional hypothesis. We have to remember our variable levels, nominal, ordinal, interval ratio, because again, that's how we choose which test to run, okay? And then we have to think about the relationships in the variables that we're looking at. There has to be some supporting evidence to say that those relationships between job title and marital status, between work-life balance and job title, are valid relationships to examine in our sample population, okay? So inferential statistics and descriptive statistics, it's about helping us make sense of our sample data using these different tests. We always begin with the descriptives, and then we can move into inferential if we have the right kind of data to look at relationships and variable attributes to determine, is this statistically significant? Is there some meaning behind this relationship in our sample population, or did it just happen by chance? That's the ultimate thing, because then we want to use that information to make informed decisions about our interventions to ensure that our clients are having the best possible outcomes. That's how this all ties back together. This is where we produce the evidence that what we're doing is having a positive impact for client outcomes. So after you review these concepts, okay, then we're going to actually move into doing the t-test with our hypothetical client data. And then after we do the t-test, we'll move into ANOVA, we'll move into chi-square. Again, this week, I want you to review those concepts. I've provided you with a worksheet. I want you to go back. You can use either this presentation, you can Google the terms, you can go back to your research book if you still have it, or any of the research books you have, to pull out the definitions and examples of those terms that are going to be so important for you to remember when you're choosing to run your inferential test. You do the worksheet, you're going to get the points for it, but then you're also going to have that as notes as you're moving forward and actually running through the inferential test in Excel on our hypothetical data. So that's what I want you to do for this week, is to review those concepts, think about where we're at, and then next week you're going to actually have an assignment where you're going to run t-tests on our sample data.